Hi everybody, John Accardo here. Welcome to part 2 of this series covering the FS200 clamp-on utility software. In part 1 of this series, we covered accessing and downloading the utility to your PC. Now we'll begin to drill down into the application and look at the various features and functions that it can offer you in working with your clamp-on ultrasonic flow meter. In this session, we'll talk about the clamp-on liquid tool, which will allow you to enter information about your application for liquid applications and determine the best transducer for the application, the installation parameters, look at the variety of different features you can access to ensure that your application is acceptable. So once you have the application up and running, if we simply go up to the Utility tab, we can begin creating our application. Keep in mind that there's no need to do any sort of setup, connection, or connection to your flow meter to utilize this section of the Utility tool. You just simply go to the Utilities tab, click it, scroll down to the Clamp-on Liquid tool, and click it to open up the window and begin creating your application. And you'll get this window to open. In this window, across the top are your preset configurations, which you can adjust to your particular requirements. So you have defaults for units, length units, so you have a choice of inches or millimeters. You have temperature choices. You have velocity, and now this applies to both sonic velocity and flow velocity. And you can choose either meters per second or feet per second. You can have a choice of density values, you can have a choice of flow volume units, and also in flow time units. So you can choose things like gallons per minute, barrels per day, cubic meters per hour, whatever might be suitable for your application. So once you've set your defaults, you can then go ahead and program in your pipe data. Now, the data that's shown on this screen is the data that was left from the last time this screen was used. The FS200 Utility remembers everything you did, and when you close the window, the next time you open it, everything that you left is still there. So obviously the last time this was utilized, I programmed in a 2-inch Schedule 40 steel pipe. So let's choose something different now. Let's choose an 8-inch Schedule 40. So by default, or actually the last pipe material used was steel, but you can see there's quite a list of different pipe materials, all the same materials that appear in your flow meter menu. At the top of the list is steel because that is actually the default pipe material in the flow meter. You can then enter your outside diameter. Now, unlike the flow meter, this does not have built-in pipe tables, so you have to know your actual pipe OD. So for an 8-inch pipe, we know that that's 8.625. I can enter that, and then I can click down in the wall thickness, and for a Schedule 40, an 8-inch pipe has a wall thickness of 0.322. Now, if you don't know the specific dimensions, most of these are available online. You can look up pipe charts for different types of pipes and get the dimensions, or you can contact Siemens Tech Support. We can send you pipe tables for various pipe materials and schedules or classes. If your pipe has an internal liner, you could also add that. You can click the liner material, choose a liner type, and if you do choose one, you can then enter a liner thickness. If you leave it at none, then obviously the liner thickness is grayed out. With your pipe information entered, you can then enter your liquid application information. So you can choose what type of liquid you have. This is all in alphabetical order, but you'll see water at many different temperatures, and that will automatically populate an associated speed of sound. So for example, right now we're at water at 20 degrees C, and you can see my estimated speed of sound, or estimated VS, is 1482 meters per second. If I choose water at a different temperature, you'll see that that value automatically changes. And if I want to work with feet per second for velocities, I can just simply change that, and it will automatically change my number into feet per second. But for speed of sound, I like to work with meters per second. It's just what I have in my brain. So let's go back and let's just choose something different. How about this is actually a diesel fuel application? So we can go to the liquid list, which has quite a number of entries, and choose oil diesel. And you'll see now automatically the speed of sound got adjusted for that particular liquid selection. If you have better information than this, you can directly enter your speed of sound here. For example, I'll put in 1370. The same applies for the viscosity. You can enter a different viscosity if you have more accurate information than the default value. And you can also enter in your specific gravity or whatever density units you're using. If you choose, you can also enter in flow rates for your application. So let's say in our application, we're going to flow between 500 and 1,000 gallons per minute. And our temperature of 60 degrees is fine for this particular application. So now that we have all our application data plugged in, we can just simply hit the calculate button and we'll get feedback on the recommended transducers and spacing and so forth. And what you'll notice here across the center is that the application shows you that the recommended transducer type or recommended sensor type is a high precision. And that's because steel is the pipe material. So for steel pipes, high precision sensors are always the recommended type. Based upon the wall thickness that we've entered, the application recommends a D1H sensor. And it also gives you the part number of that sensor. So this is a standard temperature D1H high precision, and the part number is shown here. It further recommends that you mount reflect and utilize nominal spacing offset. And then down below, you'll see that it gives you the spacing. In this case, for reflect mounting, it's giving you nominal 28. So 28 is the number you need. That's the spacing index that appears on the spacer bar when you're installing your sensors. If for any reason you don't have a spacer bar, the application also provides the LTN. In this case, it's 8.745 inches. And that, of course, is the distance in between the two transducers when they're mounted to the pipe. The app goes on to give you other application details, such as the estimated repeatability of the measurement, the speed of sound range limits. What that means is that at this particular spacing, nominal 28, the flow meter can accept any speed of sound between 870 and 1843 meters per second. So if your liquid temperature changes and your speed of sound changes, you'll still be well within the range that the meter can accept. In the center of the screen, you can see some of the application values that are a result of the parameters that you've entered. The first three you see there are cycles of delta time, which shows how much phase shift is being imparted on the upstream versus downstream transducer signals because of the flow velocities. And since our flow rates are 500 to 1000 GPM, at the low end we see that the two signals are only displaced by 0.07% of a cycle, whereas at the high velocity it's at 0.14 of a cycle. We also see the Reynolds number as a result of the flow rate and the viscosity value. The calculated Reynolds numbers are 86,000 at the low end and 172,000 at the high end, which puts you well up into the turbulent flow range, which is a perfectly good application. And we can also see the flow velocities themselves. And this flow velocity ranges from basically 1 to 2 meters per second. If we go up to the velocity drop down and change that to feet per second, it'll show us that the flow range is over 3 feet per second at the low end and almost 6.5 feet per second at the high end. Again, perfectly acceptable flow rate values. The additional data shown is the TN, which is the transit time, how long it takes the sonic beam to cross the pipe, and the TL, which is how long the sonic beam spends within the liquid. It also gives additional information about the effect of a one-cycle shift of sonic velocity, and also VF max, which is the flow rate that would cause your upstream and downstream signals to be exactly one cycle out of phase from one another. Now, the other thing that's going on here is we don't see any kind of application warnings, so everything here is good. If, for example, we put down a minimum flow of 0, we probably get an application warning. So if I hit enter now, you'll see an application problem appeared at the bottom of the screen, and a new tab appeared in the center, which is the application problem, which gives you the description of what that problem is. And when we click on that, it's simply there's an accuracy limitation at minimum flow velocity, because minimum flow velocity is 0. And obviously at 0, any error is infinite. So the meter will point that out. It'll also give you an application repeatability graph, which shows you the kind of performance you can expect. And it will also show you the information about your Reynolds number. So the flow rate, the flow velocity will cause transitional flow to be present at 9.9 gallons per minute and end at 29 gallons a minute. So once you're above 29 gallons a minute, you're out of transition and you're actually into turbulent flow. Of course, that's all dependent on viscosity. So if this was a much higher viscosity, let's say 90 centistokes, now you'll see that those values change, and you'll see that the majority of our flow is in transition. So transition starts at 386 gallons per minute and ends at 1,135. So once you're above 386 gallons per minute on this application, you're in transition the remainder of your flow range. And that's something to be aware of, because of course transitional flow is not perfectly definable and can lead to increased error bandwidth. So you could see by these little actions that I'm taking here that you can utilize this tool to play, to try different things and see how it impacts the recommendations, any application problems that may be present. Now let's go back to where we were at 2.3 centistokes for our viscosity, and let's do something different. But let's see what happens if we choose a universal sensor. So now when we choose a universal sensor, it shows us that the size D1 is appropriate, and it gives us the part number for that flow sensor, D1, and it's changed the spacing. Notice now that it's recommended minimum spacing offset, and our spacing is now minimum 22. Let's get rid of that application problem by putting the flow rate back to something reasonable. And notice when I did that and I hit enter, it reset me back to high precision sensors. As soon as I hit enter, it recalculates, it produces results that are the optimal results. So now I'll have to manually go back in and change it back to universal. So these are little things you need to be aware of when you're using the tool. Now if I hit the universal sensor size and hit the drop down, you'll notice that it gives me a series of sensors starting from D1, then D2, then C3, C2, C1, and then it goes to A1. A1 obviously is a very small sensor. It's not suitable for a pipe of this size, but the other 5 that are shown here are all suitable, and they are shown in the order of preference. Then once you hit A1, that's more or less the end of the list. Typically with universal sensors, you can use there's more than one sensor that's suitable for a given application. And in this case, it's showing you all the ones that are suitable in the order of preference. If you were to choose a sensor that wasn't suitable, like a D3, notice we get an application problem again. And if I click on the application tab, it says poor sensor match to pipe wall. So that's another indication that the application will give you if you happen to select a sensor that's not a good match to the pipe wall. Getting back to the high precision selection, again, D1H is starred, and that's really the only sensor that's suitable for this pipe. Normally, with a high precision sensor, there's only one for any given application. Lastly, should you want a hard copy of the application configuration you've just created, you can click the print button at the bottom of the screen. This will open up a dialog box that will enable you to name the file and choose the location where to save it. By default, when you click the print button, the FS200 Utility utilizes the pre-configured default printer that's set up in the application. Should you want to verify what that printer is or change it, just exit this screen and access the File drop-down. There you can choose Print Setup, and you'll see what printer is currently chosen as the default. The application does not allow you to choose the printer at the time of printing. You'll have to set it up beforehand. So you can come here, hit the drop down, choose the printer that you want, and then anytime you click print, that's the printer that will be utilized by the program. So that was a basic look at the liquid sensor selection tool and the way you can manipulate it. You can feel free to make any changes you want to see how it impacts your application. You're not going to break anything. It's really good to evaluate your application, and also it's useful to know what your spacing is, so that you could possibly go ahead and install your sensors before your flow meter is even installed and powered up. That's a summation of the liquid sensor selection tool. I hope you found this informative. Thanks for your attention, and be sure to check out the other videos in this series, which will also cover the remaining features of this FS200 utility software. Thanks. Bye-bye.
Siemens. Ingenuity for life.